Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to show you how you can find the mass percent of iron in an ore using the stoichiometry of a balanced redox reaction. So let's get into this. So in this problem we're given a 0.376 gram sample of an iron ore, and it is dissolved in acid to reduce the iron to Fe2 plus aqueous. This acidic solution of Fe2 plus is then titrated with 41.25 milliliters of 0.02140 molar KMnO4 solution. Determine the mass percent of iron in the iron ore, and here they give us an unbalanced redox reaction, and they tell us it is in acidic solution. So the first thing we need to do in order to find the answer to this question is we need a balanced redox reaction, because they're asking us, they're giving us the, where is it? The volume of one substance, KMnO4, the volume and the molarity of one substance, and they want us to find the mass of a different substance. Anytime you need to go from one substance to another substance, you need to use a mole ratio. So that's what we need the balanced equation for. However, as you may or may not know, balancing your redox reaction is not quite the same as that of a normal reaction. There's extra steps we need to do. So let's get into this. So the first thing you want to do in balancing your redox reaction is that you need to identify and label what the oxidation states of each element in their equation has. Okay, so the rule of four oxidation states, one of them is that if you have a monatomic ion, the oxidation state of the ion is the same as the charge. So here we have a 2 plus charge. So the oxidation state is a plus 2 charge. So notice that I'm writing the plus first. For charges, technically, the plus or minus comes after the number. For oxidation states, the plus and minus come before the number. It's just a technical issue, not that big of a deal, but I just figured I would point it out. Next, we have MnO4. One of the other rules is that your oxidation states of all the elements or all the atoms in your compound must add up to the charge on the compound. So here we have a -1 charge. So when we're assigning oxidation states, oxygen takes precedence. So we're going to give oxygen a -2 oxidation state because that's what it usually has. Since I have 4 oxygens, 4 times -2 is going to be a -8. So the total negative for the oxidation states of the oxygen is -8. We know that the oxidation state of manganese plus the oxidation states of the oxygens must add up to -1. So that means that manganese has to have a +7 oxidation state, because +7 and -8 gives us a -1. Okay, so we got that complete. We'll go ahead and erase this. Again, the oxidation state of a monatomic ion is the same as the charge, so this is going to be a +3 oxidation state. Same thing with the manganese. That's going to be a +2 oxidation state. So we've now identified what the oxidation states of each element is. The next thing we want to do is divide the equation into 2 halves. We're going to have a reduction half and we're going to have an oxidation half. So let's review what we mean by oxidation and reduction. So 2 things you want to remember, or one of these you should remember, is oil rig or Leo-Ger. So oil rig, oil stands for oxidation is loss of electrons. Leo is loss of electrons is oxidation. And rig here is reduction is gain of electrons, or Ger, gain of electrons is reduction. So what does this tell us? If you undergo oxidation, that means you are losing electrons. If you undergo reduction, that means you're gaining electrons. So this is why we wrote down the oxidation states, so we can determine what is losing or gaining electrons. So if we look at iron, iron starts off with a +2 charge or oxidation state, and it ends up with a +3. So it became more positive. If you become more positive, that means you lost negative electrons. So losing electrons is oxidation. So the iron has undergone oxidation because it has increased in its positive value, positive charge, positive oxidation state. Okay. If we look at manganese, manganese started off with a +7 and it ended up with a +2. So it become less positive. So it must have gained negative electrons, right? So if you become less positive, right, then that means you are gaining negative electrons and then you're undergoing reduction. So we can divide these into two half reactions, the reduction half reaction and the oxidation half reaction. So let's go ahead and do that. So here we'll write reduction. And over here we'll have oxidation. I'll erase this to give myself some room. So oxidation. And all we're going to do is we're going to separate those items that undergone reduction and those that undergone oxidation. So we said reduction is gain of electrons. So manganese, MnO4 minus, gain electrons, so that undergone reduction. So MnO4 minus, and so that's on the reactant side. And that's going to go to Mn2 plus. That's on the product side. So here's our reduction half reaction. And so then we write the oxidation half reaction over here. So the iron, we start with iron, Fe2 plus, and then that goes to Fe3 plus. So it increased in oxidation state, so therefore it lost electrons, therefore it undergone oxidation. So now that we have our half reactions, we have the reduction half reaction, we have the oxidation half reaction. So now we can balance the half reactions separately, and then we'll bring them together again. So what do you do to balance these half reactions? First thing you want to do is balance the atoms themselves. So if we look at the oxidation side, we don't care about charge right now. We'll balance charge later. That's another step. But right now, we're just focused on making sure that the number of atoms are the same on both sides like we normally do. So we have one atom of iron, one atom of iron. This is balanced as far as atoms go. Okay, let's look over here. Now we have to balance the atoms on this side. Here we have one manganese. Here we have one manganese. Again, we're ignoring the charges for now. However, here we have 4 oxygen. Here we have no oxygen. So what do? So this is where with redox reactions, you have to pay attention to acidic solution. So this is in water. It's in solution. So that means that we're going to use water molecules to balance the oxygen. So since I have 4 oxygen over here, I'm going to need 4 water molecules over here. So I'm going to add 4H2O. So now the oxygen is balanced, but now I have the hydrogen here. So I have 4 times 2 is 8. I have 8 hydrogen. How am I going to balance hydrogen? I don't have any hydrogen over here. Well, that's where the acidic part comes in. Acidic means you have H plus ions in solution. So we're going to put on this side 8 H plus ions. So now I have 8 hydrogens on this side. I have 8 hydrogen on this side. Both sides are balanced with the number of atoms. So now both of these, the reduction and oxidation half reactions are now balanced as far as the number of atoms go on each side. Now that we have that done, the next thing is we need to balance the charge. We need to make sure that both sides of both half reactions have the same charge. So let's look over here. So we have a 2 plus charge over here. We have a 3 plus charge over here. We need to make them even. The only way we can do that is to add electrons. So we got to add electrons to the right side. That's going to balance the charge. So you're going to add electrons to the side that has more positive charge. So over here I have 3 plus. If I add 1 electron, that's going to reduce this side to a plus 2, which will balance the plus 2 on this side. So let's do that. So I added 1 electron. So now the charge is balanced. Now let's go over here. Over here I have an 8 plus here. I have 8 positive hydrogens. So that's a plus 8 over here. I have a negative permanganate ion. So that's a negative 1. So 8 plus negative 1 gives me a plus 7 on this side. So I have a plus 7 total on this side, right? Because 8 plus a negative 1 gives me a plus 7. And I have a plus 2, and then I have neutral water. There's no charge on the water. So that means on this side, I have a plus 2. So I have a plus 2 on this side. I have a plus 7 on this side. I have to add electrons to the more positive side to get it down so it's equal to this side. So that means I'm going to have to add 5 electrons to this side. So I'm going to go ahead and add 5 electrons that side. So now the 5 electrons plus the 8 plus here, and then the negative here, so negative 1, negative 5, that's a negative 6, plus the positive 8 gives me a positive 2. Okay, so now both sides are balanced in charge. Okay, stage 2, last step before I add them together, I need to make sure that the electrons on both sides are equal. So this half reaction has negative 1, or has 1 negative electron. This side has 5 negative electrons. I need the electrons to cancel out when I add the half reactions back together. Notice here that I have 1 electron as a product. Here I have 5 electrons as a reactant. If I have the same number of electrons as reactants and products, they'll cancel out. So that means that I need to multiply this by 5. So that means I'm going to have 5 Fe2 plus, 5 Fe3 plus 5 electrons. So now I have 5 electrons on this side as a product, and I have 5 electrons on this side as a reactant. Now I can add the 2 half reactions together, and then the electrons will cancel out. So let's go ahead and put these back together. So here I have 8 H plus MnO4 minus, and then I got to add the reactants to the same side. So these reactants plus I got this reactant here, so I'm going to add that plus 5 Fe2 plus, and now the products. So I have these two products here. So Mn2 plus 4 H2O. And now for this product here, plus 5 Fe3 plus. And so this, ladies and gentlemen, is my final balanced equation. This is the balanced redox reaction. Notice I didn't include the electrons because they cancel out. Okay, now that I have my balanced equation, now I can do stoichiometry that's required to solve this problem. Okay, so what do I begin with? Well, what do they give me? They gave me 41.25 milliliters of a 0.02140 molar solution. Okay, so they want me to go from the KMNO4 to the iron. So I'm going to start with what they give me. They give me milliliters of the KMNO4, so I'm going to write that down. So I have 41, where is it? 41.25. So 41.25 milliliters of the KMNO4 over 1. So now I need to start converting. So I need to convert milliliters to something, and I need to get the moles. Remember, when you're doing a stoichiometry problem, the first thing you need to do is take the given unit that they give you and get it to moles any way you can. So they gave me molarity, so I can use the molarity here to convert to moles. So molarity is moles over liters. So I need to convert my milliliters to liters first. So I'm going to do that. So I know that 1 milliliter of KMNO4 solution is equal to 10 to the negative 3 liters of the KMNO4 solution. Okay, so that's going to cancel out. Milliliters will cancel out. Again, I could have used 1,000 milliliters is equal to 1 liter. It's the same ratio. I know that milli means 1/1000th. So 1 milliliter is 1/1000th of a liter, 10 to the negative 3. So now that I have liters, I can now use the molarity to convert to moles. So I'm going to do that. So I'm going to put 1 liter of the KMNO4 on the bottom, and that's the solution. Let me write solution here so I can be complete. And then the moles, 0.2140 moles of KMNO4. KMNO4. So now the liters of the KMNO4 solution will cancel out. Now I have moles of the KMNO4. So what do they want? They want grams of the iron. They want grams of the iron in the iron ore, right? So this is the mass of the iron ore. We need to find grams. Why do we need to find grams? Because what do they want us to determine? The mass percent of the iron. Well, I can't do mass percent without figuring out what the mass of the iron in the iron ore, so I need to keep going. So here, I'm going to have to do a mole ratio between potassium permanganate and the iron that I have, the iron 2 plus. Don't do this one because what do they tell us? They dissolve the iron ore in order to reduce the iron to what? Fe2 plus. So this is what we're interested in. So you could see that the permanganate ion has a ratio of 1 to 5 with the iron ion. So we're going to use that ratio. And keep in mind that permanganate, for every one of these KMnO4, you get one MnO4. So it doesn't matter if it's MnO4 or KMnO4, it's the same ratio. So it doesn't matter. So I'm going to write my mole ratio. On the bottom, I'm going to put 1 mole of the KMnO4. And then on the top, I'm going to put 5 moles of Fe2 plus. So 5 moles of Fe2 plus. So now the moles of KMnO4 are going to cancel out. Now I have moles of the iron. Now my last step is to convert to grams using the molar mass, because molar mass is a relationship between grams and moles. So I'm going to look up the molar mass of iron, 5585. So 1 mole of iron on the bottom and 55.85 grams of iron on top. Let me double check. 55.85, that is correct. So now the moles of the iron are going to cancel out. I know I have a +2 here, but I have no plus there. It doesn't matter. We're just talking about the mass of the iron in moles. So whether it's a 2 plus or no plus, it's okay. Okay, so now that I have grams, I can now calculate the amount of grams of the iron that was in the original sample of my iron ore. And when I do that, I get 0.24650. Where's my 24650? I'll write that down here. So 0.24650 grams of iron. So this is the amount of grams in the original grams of iron in the original sample of the iron ore. They want us to find the percent mass. Well, how do you find a percent? So let's remind ourselves that to find a percent, you take a part, divide it by a whole, and then that gives us a relative amount, a fraction. Well, how do you turn that into a percent? Well, percent means out of 100. Well, how do you get a percent? You take the fraction, you multiply it by 100. So you multiply this by 100, and then you get the percent. Now, it's called mass percent because the part and the whole are masses. So we're going to use grams. So what is the part and the whole that we're talking about in this problem? Well, we want the mass percent of iron. Well, iron is the part. So I have this many grams. Well, this many grams of iron is a part of the whole ore sample. What's the whole ore sample? The 0.376 grams. That's my whole. So I'm going to take the 0.24650 grams of the iron that was in the ore, and then I'm going to divide that by the total mass of the ore, 0.376 grams of the ore. And then I'm going to multiply that by 100. Now, before I do that, let's look at sig figs here. So the answer here should be in the proper number of sig figs. So when I multiply and divide here, the answer here should have the same number of sig figs as the least number of sig figs in my measurements that I'm multiplying and dividing. So here I have 4 sig figs. This is exact, so ignore that. Here I have 4 sig figs. This is exact, so we're going to ignore that. And here I have 4 sig figs. So 4 is the least number, so I should have 1, 2, 3, 4. So I'm going to underline the 5. I keep an extra digit just to avoid rounding errors. So I'm going to underline the 5 here. So when I calculate this, I can figure out what the proper number of sig figs is. And so when I calculate this, I get 65.560. So 65.560%. And again, whenever you're multiplying and dividing, your answer should have the same number of sig figs as the least number. So here I have 3 sig figs. Here I have 4, because this 0 doesn't count. So the least number is 3. So I got to cut it off at 1, 2, and 3. So cut it off after the 5. This is a 6, so I got to round this 5 to a 6. So it becomes 65.6% iron by mass. And so that, ladies and gentlemen, is the answer to this question. And I hope this is helpful to you. I hope this answered a lot of questions, and I hope you enjoyed the video. And so if you did, then please like the video, share the video, hit that like button somewhere over here, I think. Also, do me a favor, support the channel, subscribe to my channel, hit that notification bell. When you do, make sure you click all so you'll be notified by all the videos I put out. And also, finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, put that down below. If you have a topic you want me to cover, share that with me. I would love to do that for you. Thanks for joining me, and have a great day.